AP Calculus AB, Unit 10, Day 1, Office Hours. This was your assignment out of the book. There was one even problem. This is the answer to number 32 is the cube root of 4. So let's go ahead and try these problems out. So some of them came with pictures, and I personally would draw them real quick. It helps you to kind of set things up. But so number 1, the picture looks kind of like this. Quick sketch. You're finding the area of the shaded region. So there was a line that went through the origin, y equals x, and then there was a parabola. And the equation was y equals x squared plus 1. So it's just standard parabola shifted up 1. And the area went from -1 to 2. And it was, so it was this shaded area right here. Okay. So, I don't think I would consider doing this with horizontal slices. I think that would be a lot of hassle on this one. So, I'm going to set up the area. We're going to integrate. You draw one slice, y top minus y bottom, and y top in terms of x is x squared plus 1. Y bottom in terms of x is just x dx. So that's your setup. And then we're going to integrate it. Antiderivative x cubed over 3 plus x minus x squared over 2. -1 to 2. Plug 2 in. You're going to get 8/3 plus 2 minus 2. Plug -1 in. You're going to get -1/3 minus 1 plus 1/2. And you got to distribute that subtraction. So the 2's are going to cancel. And so we're going to get 8/3. And this is going to be, let's see. Make sure I didn't make a mistake here. -1. Oh, this was a negative, so it's still going to be negative. Okay. So we have, let's see, least common denominator can make it 6. So multiply by 2, multiply by 3, multiply by 6. So we have a -2, -8, -11. It's going to be 11 over 6. Getting a little different answer. And oh, you know what? I think I combined some things some different ways. Okay. So then least comes down right here. So it's going to be 16 minus 11 is 5 over 6. This is a totally different answer like that. Okay, let's double check our work real quick. I think you know, the way I did before, I was, instead of doing all this least common denominator stuff, I said, okay, well, this is going to be plus 1/3. So we have 8/3. So that's going to be 9/3. And then we're going to have -1.5. So that's 3/2. And then you could reduce this to 3. And so this would be 4.5 or 9/2. Now, what did I mess up doing it the other way? So the 8/3. Give these all these common denominators. So it's -2, -8, -11 over 6. I mean, that seems right also. But they don't, those are not the same answer. Oh, well, maybe this will make this, maybe this makes sense. It's 16 plus 11, so it's 27 over 6. which if you reduce a 3 out of the top and bottom, you get 9 over 2. Okay, yeah, we got the same answer. I just messed up right there at the end. So it is 9/2, 4.5. Okay. Number 3. Picture looks like this. I'm going to quick sketch. And so we have, let's see. Looks like we have a horizontal line, y equals 2. And then we have y equals x. And we have this other funny shape that looks like this, and the function is y equals 1 over the square root of x. And so we're trying to find this area right here. Now, we could do vertical or horizontal. I think horizontal would actually be very convenient on this one. Vertical, you're going to have to split it up here. You have to do 2 different setups. I guess we could do it both ways. If you did vertical slicing, we got to find this intersection, which would involve setting those equal to each other. And then we go at x to 3/2, x equals 1, plus or minus. This function doesn't exist where x is negative. You're raising both sides. No, it wouldn't be plus or minus. You're raising both sides to the 2/3 power. So you're not, yeah, it's an odd root. So x equals 1. So, and if you plug 1 in either one, it's 1, 1. This intersection is when y equals 2. So x equals 2. And this one is when these two intersect, should set this equal to each other. We could flip both sides, square it, x equals 1/4. So this is at 1/4, 2. All right, so we have all the intersections. We might have needed those anyways, for horizontal slicing. Let's do vertical slicing first, and then you could compare. So it's going to be y top minus y bottom, all right? Y top minus y bottom. And we're going to go 1/4 to 1 first. Y top is 2 all the time. Y bottom is 1 over the square root of x dx. And then you'd have to set up another one to go from 1 to 2. And y top is still 2. Y bottom is now x. So that's your setup for vertical slices. I think horizontal slices are going to be better. Integrate this as x to negative 1/2. So you're going to bump it up 1 to positive 1/2, divide by the new exponent. And this is going to be 2x minus x squared of 2. You go 1, 2. So you plug 1 in here, you can get 2 minus 2. Plug 1/4 in, you're going to get 1/2 minus square root of 1/4 is 1/2 minus 1. So that's the first one. And then here we're going to get 4 minus 2 minus 2 minus 1/2. So we just got to clean this all up. So this is going to be positive 1/2 is that first chunk of area. And then that's going to be 2 minus 1/2. So that's going to be half also. And so it's kind of interesting. They both came out to 1/2. They don't look like the same shape though. They just happen to have the same area. So you get answer is 1. Now horizontal slicing, the benefit of that is there's only one region. So you just got to do x right minus x left. Now x right is just going to be y, and x left is going to be, you would have to score both sides, flip them upside down. It's going to be 1 over X left is going to be 1 over y squared. dy, the limits are going to be bottom y to top y, 1 and 2. So this is the setup versus this. You get this. Simpler in a lot of ways. I feel like, easier to integrate, easier values to plug in, only one integral instead of two. So if you integrate this, it's going to be y squared over 2 minus y to the negative 1 over negative 1, 1 to 2. Could clean it up. Y squared over 2 plus 1 over y. And so if you plug 2 in, you get 2 plus 1/2. And you plug 1 in, and you get 1/2 plus 1. And so we get 2.5 minus 1.5 is 1. Same answer. A lot cleaner work, though, I think, right? I mean, compare this to this. So we should, give horizontal slicing a chance. There's certain places where it's a lot better. Okay, 5a says find the area of the region enclosed by the curves y equals x squared and y equals 4x by integrating part A with respect to x. And then that's all I had to do. I would draw a picture and so we have a parabola and you have a line, y equals 4x, that goes to the origin. And I think we're going to need to find, this is the area we're trying to find. So we've got to find the intersections. This is probably 0, 0. But if you set them equal to each other, x squared equals 4x. Move everything one side, x squared minus 4x equals 0. Factor it. X equals 0 and 4. So this is at 4, 16. So we were told specifically to do it with respect to x, which would be vertical slicing, which I think looks like a easy approach. I mean, you could do horizontal slicing, but all right. So the area is we're going to integrate left to right 0 to 4. Y top is the line 4x. Y bottom is the parabola x squared. So that's your setup. So the antiderivative is going to be 4x squared over 2 minus x cubed over 3. So you plug 4 in here and get 32 minus 64 over 3. Plug 0 in, you get 0 and 0. So this is going to be 96 thirds, right? This is going to be 32 thirds. There you go. That's your answer. Okay, sketch the region enclosed by the curves and find its area. So these ones, they're not giving you a picture done, but they're telling you to do it, probably because that's a good idea. So 7, y equals x squared, y equals the square root of x equals 1/4, and x equals 1. Okay, so we know it's going to be between these positive x's, so we could probably just focus our graph over here now. Y equals x squared is a parabola. Y equals the square root of x is the top half of a sideways parabola. They intersect. We can find their intersection right now just in case. I would square both sides to get rid of the radical. And then move everything on one side equals 0 and factor it. And you get x equals 0 and x equals positive 1. So this is 0, 0. And this is 1, 1. And we're factoring from 1/4 to 1. So just this area right here. I think y top minus y bottom makes the most sense since we have this vertical slice, vertical limits. So set up. Y top is square root of x. Y bottom is x squared. Need parentheses. Dx. We're integrating left to right. 1/4 to 1. I mean, horizontal slicing would be not very fun on this problem. That's x to 1/2, so it's going to be x to 3/2. Divide by the new exponent. Minus x cubed over 3. Power will bump it up 1. Divide by the new exponent. So we're going to get 2/3 minus 1/3. And then plug 1/4 into this. We do the square root first, which is 1/2. And then you cube it, and you get 8. And one of the 2's reduces with that, so it's going to be 2. It's going to be 1/12. Minus, if we plug 1/4 in this, the 4 gets cubed. That's 64 times 3 is 192. So 1/192. Okay, so this is going to be 1/3, and this is going to be the least common denominator here would have to be 1 times 12 equals 192. 10, and then you have another 72, which would be 6. So 16. So that's going to be 16 minus 1. That's going to be 15. So it's going to be minus 15 over 192. 3. We can divide a 3 out of both of these, I think, just to make the number smaller. But actually, I don't know if we want to do that. If we did that, we get 5 over 64. But then we want to give these least common denominators, which would be 192. So we're going to multiply this by 64. So we have 64 minus 15 be 59. 49 over 192. So, little ugly numbers there at the end. Number 9, y equals cosine 2x. Y equals 0, x equals pi over 4, x equals pi over 2. So let's get a drawing going here. It's a cosine curve, which you guys should be, break it up, chop it up into halves. So this is usually 2 pi, but there's a 2 here, so it gets divided by 2. So the period is pi. And the cosine curve starts here at 1, it goes to 0, it goes to -1. This is at pi over 2, goes back up. All right, so quick sketch. Now y equals 0 is the x-axis. Pi over 4 is right here to pi over 2. So we're trying to find this area right there. And we're actually trying to find the area. So if we integrate this, it's going to come out negative. So we've got to fix it. So the area is going to be pi over 4 to pi over 2. But it's going to come out negative. Now, this is a chain rule issue here. It's going to be sine of 2x, but it's going to put an extra 2 out in front. You could easily use substitution, or you could just put a 1/2 to fix it. Sine of pi is 0. Sine of pi over 2 is 1. So the answer is 1/2. There we go. All right, 13. Y equals e to the x. y equals e to the 2x, x equals 0, and x equals the natural log of 2. Okay, well, y equals e to the x is an exponential, right? It goes through 1. 0, 1. Has a horizontal asymptote, x equals 0. Y equals e to the 2x also goes through 1, but it's steeper. It's going to go faster, so it's going to kind of look like this. This one's going to be on top. And we're going from 0 to natural log 2. Now, natural log of 2, some positive number, right? And so we're trying to find the area between these. And this one's for sure on top. I think we're going to do vertical slices. So y equals e to the 2x is on top. Y equals e to the x is on the bottom. E to the 2x grows faster. They both go through 0, 1. Okay. So, all right, let's do it. So area equals y top minus y bottom, vertical slices. E to the 2x minus e to the x dx, integrating left to right, 0 to natural log of 2. So antiderivative is going to be e to the 2x, but an extra 2 is going to pop out. So I put a 1/2 there to fix it, or we could do u substitution and do that. That's e to the x. So e to the 2 natural log of 2 minus e to the natural log of 2 minus 1/2 e to the 0 minus e to the 0. Those are going to become 1s. Now, this, we can't cancel the e in the natural log like this. There can't be a number in front. So you bring that in as an exponent. Now it's e to the natural log of 4. So that's going to be 4. So it's 1/2 of 4 minus 2 minus, this is 1/2 minus 1 is going to be negative 1/2. So that's going to be 2 minus 2. Those cancel out, and we get positive 1/2 for the final answer. That's it. 1/2. All right. 17. This one's crazy. Y equals 2 plus absolute value of x minus 1. Y equals negative 1/5 x plus 7. This one seems kind of crazy. Okay. We could, let's see. So this is a V graph that's been shifted to the right 1. So usually it'd be down here. It's an absolute value graph. But it's been shifted to right 1 and up 2. Right 1, up 2. So this is the new vertex of that graph. And then it goes up 1 over 1 on both sides. So it looks like this. And then this graph has a y-intercept of 7. 1, 2, 3, 4, 5, 6, 7. And it has a slope of negative 1/5. So it goes down 1 over 1, 2, 3, 4, 5. I think it might actually be at a nice dot there. And then it goes up. You could go backwards. You go up 1 over 5. Up 1 over 5. 1, 2, 3, 4, 5. So I think they might actually intersect at nice points, which would make life a little easier. And so we're trying to find this area in between. It's just drawing that is kind of hard. I think integrating is not going to be bad, but I mean, to find these intersections would be a bit tougher algebraically. Now, this, what we could do is you could write the equations of these lines separately. So when x is bigger than 1, it's like you just drop the absolute values. When x is less than 1, then you have to take the negative of what's inside here. So it's going to be negative x plus 3. And that should look right based off of our graph. Like this looks like a line that goes through 1 with a positive 1 slope. This looks like it goes through 3 with a negative 1 slope. So I think that would be helpful. And we're going to split up our calculation right there. So we're going to do this half, and then we're going to do this half. And we're going to do y top minus y bottom. But y bottom changes once we get past this. So our setup is going to be what? And if we did horizontal slicing, you'd have to have 2 separate intervals anyway. So there's definitely no advantage to horizontal slicing. So I don't think I'm going to go through the process of having to try to figure those out. Now, these intersections, was this at 5, comma, because we started when we went down 1/5. So 5, if you plug 5 into both of these, we could confirm that this is actually the intersection. So if you plug 5 in here, we get 6. And if you plug 5 in here, you also get 6. And then negative 5, you would get 8. And negative 5 here, you get 8. So that's good. And then this intersection right here is at 1, 2. All right. So we're going to integrate y top negative 1/5 x plus 7 minus y bottom. Y bottom was this, negative x plus 3. I'm putting things in parentheses, just make sure I distribute this all correctly. And we're going from negative 5 to 1. And then the next one, y top is still negative 1/5 x plus 7. Y bottom, though, is x plus 1. And we're going from 1 to 5. So that's our setup. Now, I'd probably clean this up. This is going to be positive 4/5 x, right? Positive 4/5 x, and then 7 minus 3 is 4. So we just treat it like that. And this one is going to be negative 6/5 x plus 6. So the antiderivative of this is going to be 4/5 x squared over 2 plus 4x. Antiderivative of this one's going to be 6/5 x squared over 2 plus 6x. So then we plug 1 in, and we get 2/5 plus 4. And then we plug negative 5 in, and we get positive 25 over 5 is 5 times 2 is 10 minus 20. Wow, little numbers here. Plug 5 in here, get 25 over 5 is 5. It's going to be negative 15 plus 30. And then we plug 1 in, and we get negative 3/5 plus 6. Okay, so you just got to be careful here, I guess. Let's see, this is going to be negative 10, so it's going to be positive 10, 14, and 2/5. This is going to be 15. Minus 6 is 9. 9 and 3/5. And so it's going to be 23 and 5/5, or nicely 24. Worked out good. 24. That one's a test of details. All right, a few more. A couple of these new ones that we talked about in the lesson. So 31 says to find a horizontal line, y equals k, that divides the area between y equals x squared and y equals 9 into 2 equal pieces. Now, it doesn't have to always be equal. It could be like 1/3 and 2/3, or, but for now, we'll simply go with 2 equal pieces. So I think we need to draw a picture. This is parabola. And horizontal line, y equals 9. So this is the area. And then we want a horizontal line that cuts it exactly in half. So that's our strategy. So let's see, we got to find the total area first, right? So, and these intersections are 3, 9, negative 3, 9. So finding the area, we could do with vertical or horizontal slices. Now, the fact that we're going to do horizontal slices eventually might make you want to just start with horizontal slices. It might just save you effort because you're going to have to set it up that way anyways. But I mean, if you did vertical slices, y top minus y bottom, just to find total area, it's going to be the same area any way you slice it, right? Literally. So y top is 9, y bottom is x squared dx. And so we get 9x minus x cubed over 3. So we get 27 minus 9 minus negative 27 plus 9. And so we get, we have, well, this is going to be 18 minus negative 18. So we get 36. That's your total area. But for the next part, you're going to have to set up horizontal slicing no matter what. You have to do x right minus x left. Now, finding x right and x left, they're both on the parabola, so you would solve for x in terms of y, and x right is going to be the positive square root of y, and x left is going to be the negative square root of y. They're both sides of the same curve. One's the positive, one's the negative. These are positive x's, these are negative x's. So we're going to have to do x right minus x left, square root of y minus negative square root of y, dy. And we're going to go 0 to k, or k to 9, but 0 is going to be easier. Now, we could have just started with this strategy and said, oh, well, let's find the area with horizontal slices because we're going to have to do that for the next part anyways. Might as well just not have to rethink about it in from two different ideas. And we'd say 0 to 9 here. And then all the work we do here would be work that would be similar here, and you just kind of take advantage of it. Now, this is going to be 2 square root of y, which is y to the 1/2. So it's going to be y to the 3/2 divided by the new exponent. So it's going to be 4/3 times square root minus 3 cubed is 27 minus 4/3 times 0. And you get 36. Same thing. Now we're going to do the same thing, 0 to k. So it's going to be 2, 0 to k, square root of y, plus plus. Antiderivative is going to be y to 3/2 divided by the new exponent, 2/3. Right? We're going to set it equal to half of the area. Right? Half 36 is 18. Okay, so we're going to have 4/3 plus k to the 3/2 minus 4/3 times 0 equals 18. And we can totally solve this without a calculator. Multiply both sides by 3/4. So it's going to get 27 halves. We're going to raise both sides to the 2/3, which is a cube root and a square. So no plus or minus this time. The cube root of 27 is 3. Cube root of 2 is cube root of 2. And then you're going to square it. So we're going to get 9 over the cube root of 4, which is fine as your answer. Now, if you really want to simplify it, you can multiply top and bottom by cube root of 2. You get 9 cube root of 2 over 2. That's another version of the answer. There you go. All right, 32. Let's find a vertical line that divides the area between x equals the square root of y, x equals 2, and y equals 0, into 2 equals y. So we're trying to find a vertical line y equals k that cuts it in half. Now to graph this, I'm going to reimagine this as y equals x squared, right? So this is really just the right half of a parabola. And we're going to, so it says y equals 0 and x equals 2. So y equals 0 is the horizontal axis, the x-axis. So that's the area we're looking at. And we're trying to find a vertical line, x equals k, that cuts it in half. I think doing vertical slicing is going to make the most sense because we're eventually going to want to have to do that anyways. So the setup is going to be, I've got to find the total area first. So 0 to 2, y top minus y bottom. It's going to be just x squared. So x cubed over 3. 0 to 2, 8 thirds, minus 0 thirds is 8 thirds. So that's the total area. And now we need to set it up to where I'd say 0 to k of x squared dx. So we want to integrate this gradually until we get to half of 8 thirds, which is 4 thirds. Right? So we're going to integrate both sides. We're going to integrate it. We're going to get k cubed over 3 minus 0 over 3. Can multiply both sides by 3. And then we're going to take the cube root of both sides. No plus or minus. So k equals the cube root of 4. There you go. All right, last problem. It says 41. The accompanying figure shows velocity versus time curves for two cars that move along a straight track, accelerating from rest at a common starting line. So I'm going to draw this picture real quick. So got some big values all the way up to 180. This is velocity, feet per second, versus x, or time. And then, so they both start at velocity of 0. This one is curved upwards, which looks a little more realistic than this. No, this one maybe is already going. It says from rest. So this isn't very, I don't think that's realistic. That's fine. As a velocity curve, this is fine. Okay, so one of them is 3t, and one of them is t squared over 20. All right. Says, how far apart are the cars after 60 seconds? So distance, how far apart, is the absolute value of velocity. But it's got to be the differences. We want to find the differences in their velocities this whole time. So to find the distance between them, we would integrate the absolute value of the differences in their velocities. Now, this is going to be a little simpler because we know how to make this positive for sure. So we don't have to do any of the tricky stuff. We can just say, oh, well, it's going to be velocity 1 minus velocity 2, because velocity 1 is always above velocity 2, at least for the time that we're concerned with, 0 to 60. Right? As you plug 60 into both these, you get 180 for this guy, and 60 in here would be 3,600 divided by 20 is going to be 180. So we don't have to get too crazy with the absolute values. So then, let's see the values. So this is what, 3t. And so the antiderivative is going to be 3t squared over 2 minus t cubed over 60. 0 to 60. Plug 60 in here. It's going to be okay. So one of those 60s cancels. This gives you a 30. So that's going to be 3,600 minus 3,600. Or did I make a mistake? Let's see. Oh, yeah. This is 3 times that. So that's going to be 4,200. Is that right? No. Let's see. 9 times 6, that's 5,400. 5,400 minus 3,600 is 1,800 feet, units. All right. That's part A. Part B says how far apart are the cars after t seconds, where t is 0 to 600. Well, it's the same idea, right? We're going to go 0 to t, and t is between 0 and 60, so we know that the top one is always v1, the bottom one is always v2, so we don't have to worry about the absolute values. This will make sure it's positive. So 3t squared over 2 minus t cubed over 60. And then you're going to plug t in. So it's going to be 3 halves t squared minus t cubed over 60. And you plug zeros in, they drop out, and the units are feet. It's actually easier. We didn't actually have to plug any real numbers in there. So that's part B. Okay, that's the assignment. A lot of details.